Okay, so now in this video, let's do a couple of examples related to these LCM and HCF and so on and so forth, so we are comfortable with them, and then we can move on to the next things over here. So let's see what we have. So the LCM and HCF, foreign pairs of integers 25. Okay, so for example, let's say that you want to find the LCM and HCF of 26 and 91. So you have these two numbers, 26 and 91. So you want to find the LCM. You want to find the LCM and HCF of these two numbers. How do you do that? So basically, in order to do that, there are a few ways that you can actually do it. So first, you can actually prime factorize these numbers and then use the methods that we talked about before to analyze the numbers and then find the LCM and HCF. The other way, there is another way that you can do it, and that is basically by way of the Euclid's division algorithm. Okay, so we will do a couple of them using basically prime factorization, and a couple of them using Euclid's division algorithm. Okay, and that way we get to appreciate also how Euclids have made things much easier for us. Okay, so for example, 26, you know that 26, if you prime factorize it, you get 2 times 13, and 91 is actually one of those special numbers. If you go to, there is a website over here, and if you check for basically 91, you will find out that 91 is actually divisible by 7 and 13. I like these kinds of numbers. These are, I don't really know how to say, what sort of, I have this kind of, for example, I have different categories for numbers in my mind. For example, 91, which was 7 times 13, This is one of those special numbers, and you cannot find many such numbers in basically all of the numbers that we know, compared to, for example, odd numbers or even numbers and so on and so forth. Their number is not that high. Okay, so that is that. So then basically 7 times 13. So now how you basically find the LCM of these two numbers. We said that your LCM, now let me first do this and then I'll tell you how you can do that formally as well. So when you want to find the LCM of these two numbers, 26 and 91, basically you're looking for some number that contains both of these two numbers, meaning that for the 26 you need a factor of 2 and a factor of 13. So that's a 26. And also for a 91 you need a factor of 13 and you need a factor of 7. So then the factor of 13 I already have it. The factor of 7 I can write it over here, and that's basically the LCM of these two numbers. Now if you pay attention to how you did this over here, it is actually the least number of, or the smallest number of, the smallest power, not the number. The smallest power of the smallest power of prime factors. Prime factors related to both numbers. Okay, so what that means is that the prime factors of these two numbers are 2, 7, and 13. All of them put together, related to both the numbers. And of course, it doesn't matter whether you had 2 numbers or 3 numbers or 1,000 numbers, you would have a number of prime factors related to all of those numbers. And then you would take the smallest power of prime factors related to both the numbers. So for example, over here, you have a 13 over here. So here basically you have 2 times 13 raised to the power 1, and over here you have 7 times 13 raised to the power 1. So the smallest factor of 13 here is, for example, in case the factor is common between the two numbers, you take the smallest power of the prime factor, which is right now 1 and 1, so you take any one of them. So that would be 13 raised to the power 1 times 2 raised to the power 1 times 7 raised to the power 1, and that gives you this number, which is equal to 14 times 13, which is equal to 12, 1, 42, 14, 182. So that's equal to 182 as the LCM of these two numbers. Now about the HCF of these two numbers, and some people call this this stands for the highest common factor. Highest common factor. Actually, this is supposed to be an uppercase F. So some people, this stands for the highest common factor. Some people also refer to the same concept by using the word the greatest common factor, which is this stands for the greatest common factor. So what you do here is basically you once you have the two numbers that you want to take, the highest common factor of, or HCF of. So what you do is basically you go for the basically you want to basically pick all the numbers between these, all the factors between these two numbers that are basically common. So you have a factor of 13 over here, you have a factor of 13 over here, so they are in common, so you can pick them. And of course 2 and 7 are not common, so you don't pick them. So the HCF of 26 and 91 therefore is equal to 13 raised to the power 1, which is equal to 13. Now if you pay attention to how I did this over here, this is on the other hand the greatest power. This is the greatest power of common factors. I think before formulating this, I need to basically see a few more examples, because I always forget this formal way of referring to this, so I don't want to make any mistakes. But once we get through some other examples, I will give you a formal definition for that as well. So that's basically 13. Now the HCF and LCM of these two numbers are 13 and 182. And in the previous video we said that what was that? There was a relationship between the HCF HCF of two numbers, between the LCM of two numbers, and between the two numbers that you are taking the HCF and LCM of. Meaning that if you take your two numbers as A and B, and if you multiply those two numbers, that's always equal to the HCF of A and B times the LCM of A and B. Okay, so this relationship is actually always there. This relationship is actually always there. So you can use this relationship everywhere. Meaning that the two numbers that we had were 26 and 91. So I can write 26 times 91. It's supposed to be equal to the HCF, which is 13, times LCM, which was 182. And you can test this. So for example, 26 times 91. 26 times 91 is equal to 6. And that's 54. And that's 218. So that's 6, 13, and 2366. 2366 is equal to 13 times 182. 182 times 13 is equal to 6. 24, 2, and 5, and that's 182. 6, 13, and 2366. Okay, so you see that this relationship is actually valid between the HCF, between the LCM and the two numbers, right? Now the next thing that we have here is I have two more numbers. For example, 510 and 92. 510 and 92. These are the two numbers I want to take the HCF and LCM of these two numbers. So how do I do that? So what I can do is that I can I will do this also by prime factorization, okay? And I will do it also by using the Euclid's division algorithm as well, so that we have an opportunity to see both of prime factorization method. Although we have enough examples here, so let's see how it goes. So for example, if you have 510, if you prime factorize this number, you'll get 2 times 250, 255, and 255 is divisible by 5, and that is basically 5 times 5 is equal to 25, 0, and that's a 51. So 5 times 51 is equal to 255. I think 51 is a prime number. I cannot factorize it anymore. 51 is not a prime. 3 times 17. Oh, okay, good. So 5 plus 1 is equal to 6. So this number is actually divisible by 3. So 3 times 17 is equal to 51. So then basically 510 is equal to 2 times 3 times 5 times 17. Okay. Now 92 is equal to 2 times 45, 46. This is 2 times 23. And 23, I suppose, is a prime number. 23 is a prime number. Excuse me. 23 is a proven prime. Okay. So then 92, you can write it as 2 times 2 times 23. Okay, so now the LCM of these two numbers, the LCM of 510 and 92 is equal to, you want to basically find some number in which both of these numbers can be found, meaning that for a 510 you need a factor of 2, you need a factor of 3, you need a factor of 5, and you need a factor of 17. For a 92 you need 2 factors of 2, so one of them is already here, so I write 1 factor of 2 and I already have 2 of them, and a factor of 23 and a factor of 23. So the LCM of these two numbers is actually 2 raised to the power 2 times 3 times 5 times 5 times 17 times 23. Okay, and well, I don't really know if you really want to multiply all of these numbers together. Let's leave them as they are. The HCF of these two numbers is equal to of these two numbers 510 and 92 is actually equal to the common factors, the highest common factor, meaning that you look for the common factors, which in this case basically is 2, and the highest common factor is 2 raised to the power 1, right? It's 2 raised to the power 1, which is equal to 2. Okay, so again here I need to actually go back and take a look at how I formulated that. I mean that there was something I said about the greatest common whatever and the smallest whatever. I always forget that. Let me go back over there, take a look at that thing, and then come back here, and then we will talk about that again, and then we will move on to the rest of the things. Okay, so now I know that I'm going to actually forget this soon, so I'm just going to make a note of this and even probably write it on my blog so that I can go back to it whenever I need it. So the HCF is actually the smallest powers of common factors. So the smallest power of common factors, which makes sense. The smallest powers of common factors and the LCM is actually the greatest power of prime factors, is the greatest powers of prime factors. Okay, so that is that. So the greatest power of powers of prime factors. So here the prime factors over here we have for example 2 raised to the power 1 and times 3 raised to the power 1 times 5 raised to the power 1 times 17 raised to the power 1, and over here I have 2 raised to the power 2, and here I have 23 raised to the power 1. So now the greatest powers of prime factors, here I have basically the prime factors over here. I have 2 and 2, and here I have 2 raised to the power 2, 2 raised to the power 1. So I take 2 raised to the power 2, which is the greatest powers of the prime factor 2. So that's about 2, and then the next factors are not common, so you can just write them as they are. So 3 raised to the power 1 and 5 raised to the power 1 and 17 raised to the power 1 and 23 raised to the power 1, which is basically this thing over here. So that is that. So now I know the LCM of my numbers, which is basically this number over here, and I have the HCF of my numbers. So then we said that the two numbers, if you take them as A and B, the product of those two numbers is going to be equal to the LCM of those two numbers times the HCF of those two numbers. Okay, and so the numbers were 510 times 92, and the LCM was this thing over here, so 2 raised to the power 2 times 3 times 5 times 17 times 23, and the HCF was 2. And if you do this calculation, you will get, so 51 times 92 is equal to 92, 0, 10, 1, 45, 46, so 4692, 4692, and then this is a 15 times 2 is equal to 30, 30 times 4 is equal to 120, 120 times 17 times 23. So I had a 0 over here as well that I forgot. I'm sorry. So I have 120 times 17 times 23. So 12 times 17 is equal to, and remember that I have a 0 over here. 12 times 17 is equal to 14.1 and 7, 8, and that's a 12, 4, 0, 204 times 23 is equal to 12, 6, 0, 8, 0, 4. So that's a 2, a 9, a 6, a 4, and a 0, 469920. 46920. So you see that the product of the numbers is equal to the product of the LCM and the HCF of the two numbers. Now let's do the next exercise using the Euclid's division algorithm. So you have, for example, 336 and 54. Okay, so in order to use the Euclid's division algorithm to find the HCF of the two numbers, HCF of 336 and 54, what you need to do is basically you have 336 and 54. So this number is bigger than this number. Take this as A and take this as B, meaning that A is greater than B, right? So then you have to divide 336 by 54 and find a way to express 336 in terms of 54. Okay, so if you divide 336 by 54, what you will get is 5 times would be 250, 6 times would be 24, 324. Okay, so 6 times would be 24, 2, 32, and then you have a 2, you have a 1, so 12 remainder. So you can write 336, you can write it as 54 times 6, or 6 times 54, plus the remainder, which is 12, okay? And then you need to take the divisor and divide it by the remainder in this division, because and the reason why you have to do that is that because your remainder is still not 0. If the remainder was 0, you wouldn't have to do that. So 54 If you divide it by 12, you get 3 times 4 times 48, and 48 plus 6. So 4 times 12 plus 6, so 48 plus 6 is equal to 54, right? So 54, you can write it as 4 times 12, 4 times 12 plus 6. And now you need to, actually it's a good idea to actually write the division, because actually you might make a mistake here. So I simply write 54 divided by 12, or 54 divided by 12. So it's equal to 4 times 12 is equal to 48. And then you have a 6 remainder here. So now again the remainder is not 0. So you take the divisor and divide it by the remainder. And then 12 divided by 6 is equal to 2. 12, 0. Now the remainder is 0. Now the remainder is 0, so you have to stop. So I write this over here. 12 is equal to 2 times 6 plus a 0 as a remainder. And now that the remainder is 0, at this stage, the divisor is your HCF. HCF of the two numbers you started with. HCF of 336 and 54. Okay. So now what that means is that 6 is basically your HCF. So that means that your HCF of 336 and 54 is equal to 6. Is equal to 6. And now you can actually use that relationship. A times B is equal to the HCF of A and B times the LCM of A and B to find your LCM, because you know your HCF, you know the two numbers, so you can calculate this one. So I can come over here, write 336 times 54 is equal to the HCF of the two numbers, which is equal to 6, times the LCM of 336 and 54. So that means that the LCM of 336 and 54 is actually equal to these two numbers, multiply 336 times 54 divided by 6. And I think if you divide by, this number is divisible by 6, I suppose. 6 times 9 is equal to 54. 6 times 9 is equal to 54, if I'm not mistaken. Sometimes I make mistakes in multiplication. So 6 times 9 is equal to 54. So that's a 9, and that's a 1. And then 9 times 336. So 9 times 6 is equal to, again, 54. 9 times 3 is equal to 27. 27 plus 5 is equal to 32. 3. 9 times 3 is equal to 27, and plus 3 is equal to 30. So that's 3024. So the LCM of 336 and 54 is equal to this number 3024. Now, in order to make sure that you haven't made any mistakes, this was my, where is it? This was my HCF and this was my LCM. So you can find some website to give you the greatest common factor, greatest common divisor, highest common factor, greatest common denominator. I think GCD is the same thing as LCM. Let's see what this is. For information, CR Euclid's algorithm calculator. So I think you can go somewhere over here. There is no link in here. But anyway, let's calculate the GCF, or greatest common factor, of 336, 336 and 54. If you calculate that, it's going to give you a 3 for the values 40. Oh, this is a 45. What's wrong with this thing? 54 and 336 is a 6, basically. Your GCF is a 6. Or actually the same thing as HCF. Okay. And I think the LCM, let me see if I can find some calculator for LCM. LCM calculator online. LCM calculator. It's from the same website. Least common multiple LCM calculator. So if you have 336 and 54. 336 and 54. The LCM is 3024. 3024, which is this number over here. Okay. So that's basically these two numbers over here. We can do one more of these, and then get to the rest of our work here. Okay, so the next question that we have is, given that HCF of 9. Okay, so let's do a couple more of these, and then we have another question that is also interesting. Okay, so let me go over here. And for example, you want to find the LCM and HCF of 12, 15 and 21. 12, 15 and 21. Okay. So, and if you want to do that with prime factorization, what you can do is that you can write 12 as 4 times 3, which is 2 times 2 times 2, so that's 2 squared. Let me write it this way. You can write 12 as 4 times 3, which is equal to 2 times 2 times 2 times 3, which is equal to 2 squared times 3. And 15, you can write it as 5 times 3, which is equal to 15. And 21, you can write it as 3 times 7. Okay. So now the LCM of this of these three numbers, the LCM is basically the LCM of 12, 15, and 21 is actually a number that contains basically all the three numbers, but you don't have any extra factors there. So for the 12, you need 2 raised to the power 2 and a 3. So 2 raised to the power 2 and a 3 is basically a 12. A 15 is a 5 and a 3. So a 3 I already have. So I already need a 5 for a 15. and the 21 is a 3 and a 7. So I already have the 3, so I add the 7 over here. So it's equal to 35 times 12, which is equal to 10, 1. So that's a 7, and 0, 35. So that's 0, 2, and 420. That's 420. Now, what we said about the LCM, it's the greatest powers of the prime factors. The greatest powers of the prime factors. So the greatest powers of the prime factors here, the prime factors are 2, 3, 5, and 7. So here you have 2 raised to the power 2, 3 raised to the power 1. And here you have 5 raised to the power 1, 3 raised to the power 1, 3 raised to the power 1, 7 raised to the power 1. So the greatest powers of the prime factors, the prime factor 2, the greatest power of the prime factor 2 is 2 here. So if I were to rewrite the LCM using this definition, I would write it as 2 raised to the power 2, the greatest power of this prime factor, times the greatest power of 3 over here is 1, so I write it as 3 raised to the power 1, and the greatest power of 5 here is 1, so 5 raised to the power 1, and the greatest power of 7 is 1, so I write it as 7 raised to the power 1. So that's basically the same thing, 2 raised to the power 2 times 3 times 5 times 7. Now the HCF of these three numbers, HCF of 12, 15, and 21 is actually equal to, is basically you have to go for the common factors, meaning that 2 is you have a factor, 2 factors of 2 over here, but you don't have it in these two numbers. You have a factor of 3 over here, you have it in these two numbers as well, and here you have 1 factor of 3, 1 factor of 3, and 1 factor of 3. So totally you'll have just 1 factor of 3 over here. So that's 3 raised to the power 1. And over here about the HCF, we said that it is the smallest powers of the common factors. The smallest powers of the common factors. So the common factors here are 3 and 3 and 3. So except for 3, you don't have any common factors here. And here you have 3 raised to the power 1, 3 raised to the power 1, 3 raised to the power 1. So there is no smallest or greatest. They're all equal. So you just write 3 raised to the power 1, and that's basically your HCF. So we can do another example here. So for example, you have 17, 23, 29. You have 17, 23, and 29. So these three numbers are all basically prime numbers, so there is no question of prime factorization, meaning that if you go over here, the numbers are 17. The numbers are 17 is a proven prime. 23 is a proven prime, and 29 is also a proven prime. Okay, so in such cases basically what happens is that the LCM and HCF is going to be, so you know that 17 is the same thing as 1 times 17, and 29 is the same thing as 1 times 29, and 23 is the same thing as 1 times 23. Okay, so now the LCM of these two numbers, of these three numbers, actually 17, 23, and 29, is equal to basically you want to find, you're looking for a number in which you can find the three numbers. So that's actually 17 times 29 times 23. Okay, and when you go for the, and that's actually the same thing as the greatest powers of the prime factors, the greatest powers of the prime factors. So the greatest power of 17 here is 1, the greatest power of 29 is 1, and the greatest power of 23 is 1. So 17 times 21 times 23. The HCF over here of these three numbers, 17 times 23 times 29, is equal to, you're looking for the common factors here, which is only 1. So the HCF of these three numbers is actually only 1. And that's basically the smallest power of the common factors. The smallest power of the common factors is the smallest power of 1, which is 1. So that's 1 raised to the power 1 is equal to 1. So basically, when you have three numbers where the three numbers are all, or three or two or more numbers where those numbers are all prime numbers, the LCM of those numbers is always the product of all of those numbers, and the HCF of those numbers is equal to 1. Let me actually go over here and see if I did this right. So here I have 1.2 number 3 part 2. Number 3 part 2 is 1, right? HCF is 1. Okay. And the next numbers that we have, let's do another one of these, which is 8, 9, and 25. So if you have these three numbers over here, 8, 9, and 25. So 8, you know that it's equal to 2 cubed. And 9 is equal to 3 squared. And 25 is equal to 5 squared, right? So, so then your LCM, the LCM of these numbers 8, 9, and 25 is equal to, basically for an 8 you need 3 factors of 2, so 2 cubed. For a 9 you need 2 factors of 3, so 3 squared, and for the 25 you need 2 factors of 5, so 5 squared. So that's basically the greatest powers of the prime factors. The greatest powers of prime factors. Okay. The HCF of these three numbers is basically the common, you need to go for the common factors, which is basically the HCF of 8, 9, and 25 is actually equal to, you need to go for the common factors. So here you have basically 3 factors of 2, 2 factors of 3, 2 factors of 5. So you have nothing common except for 1. So that means that the HCF of the three numbers is 1, and that's basically a case where the three numbers, or basically 2 or more numbers, have no common factors at all. So that's the smallest power of, that's the smallest powers of common factors. common factors. Okay, and let me see if I did this right. Number 3, part 3, which seems to be right. Okay, now let's see if we have anything which is also important here. So let me take a look at these exercises and I'll be back in just a few moments. Okay, so the next question that we have here is basically we know that the HCF of 306 and 657 is equal to 9. You want to find the LCM of the same two numbers, 306 and 657. 657 is equal to what? So you can use that property of the relationship between HCF and LCM and write this as and you know that HCF of A and B times the LCM of A and B is actually equal to A times B. Okay, so now the two numbers that I have are 306 and 657. So 657 times 306 is equal to 6 times, or let me actually write them the other way around, that would be easier. So I write this as 306 times 657. So 6 times 7 is equal to 42. 6 times 7 is equal to 42. 7 times 6 is equal to 42. 7 times 6 is equal to 21. 0. 5 times 6 is equal to 30. 15. And 2 zeros. 6 times 6 is equal to 36. And 18. And then you have a 2, you have a 4, 10, 1. So that's 8 plus 3 is equal to 11, 1. And that's a 0, 2. So that's 201,042. So so that means that the HCF of 306 times and 657 times the LCM of the same two numbers, 306 and 657, is actually equal to 306 times 657. Now the HCF of these two numbers is equal to 9. The LCM of these two numbers we want to find, 306 and 657, is equal to the product of the two numbers, 201,042. 201,042. So that means that the LCM of 306 and 657 is actually equal to 201,042 divided by 9. And this number is I don't know if this number is, let me see, 4 plus 2 is equal to 6, 6 plus 3 is equal to 9. So it can be divisible by 9. So 201,042 divided by 9 is equal to 2 times 9 is equal to 18. 21. 2 times 9 is equal to 18 and 3, 0. 3 times 9 is equal to 27. And 3, 4. 4 times 9 is equal to 36. 3 times 9 is equal to 27. And a 7. And a 2. And 9 times 6 is equal to, I always forget the multiplication table for 9. So 9 times 6 is equal to 54. 9 times 7 is equal to 63, and 9 times 8 is equal to 72. So 8 times 9 is equal to 72. 72 and 0, so your number is 22338. So that's 22338. So that's the LCM of the two numbers. Okay, so that's that. Let me take a look at this number 4. Let me see. Number 4, 22338. Okay. And we have a couple more examples here for a natural number n plus 13 is equal, and these numbers are composite numbers. Okay, so let me take a look at the other examples and I'll be back in just a few more. Okay, there is another example here which is actually not that important, but I mean, if you can actually solve this problem, that means that you have understood all of the concepts that we have talked about in the previous video, the Euclid's division algorithm and division lemma and so on and so forth. I just want to show you how you can actually, how this thing actually goes. Otherwise, it's not really that important. So the question is, check whether 6 raised to the power n can end with the digit 0 for any natural number n. And it can be actually useful in some circumstances. You want to know if you have 6 raised to the power n, that this number can end with a digit 0. So for example, if you have 6 raised to the power 1 is equal to 6, 6 raised to the power 2 is equal to 36, 6 raised to the power 3 is equal to some number, 6 raised to the power 4 is equal to some number, and then n can be n can be any natural number. Okay, natural number. Okay, n being any natural number, and you have 6 raised to the power n, you want to know if 6 raised to the power n can end with some number. I'm sorry, if 6 raised to the power n can end with a digit 0, meaning that the unit place in these resulting numbers can be a 0. And the way that you can solve this problem is actually you don't actually have to use the Euclid's division algorithm or the Euclid's division lemma. You can just simply solve this problem by taking a look at how you actually do simple multiplication in simple multiplication with natural numbers. So for example, if you have, let's say that you are multiplying two numbers together, and then you are getting and then you're getting some number over here. You will get some digits over here. Okay, you get some digits over here, and this is the unit place. And I want to know if I can have a 0 over here if basically the numbers that I'm multiplying together is 6 raised to the power n, meaning that 6 times 6 or 36 times 6 or and so on and so forth. I don't know what 6 cubed is actually. So so the way that you can do this, so you have basically to get this first digit over here, you have you have basically these two digits, and you have to multiply them together, and you will get some digit over here, right? You get some digit over here, and then when you for example, let's say that you are multiplying, for example, 2524 times 326, for example, right? So you're multiplying these two numbers. So So if you pay attention to what you do here, you can actually solve this problem pretty easily, because when you start your multiplication, you start with multiplying 6 times 4, the first digit over here times all the digits in this number. So 6 times 4 is equal to 24, a 2. 6 times 2 is equal to 12, plus 2 is equal to 14, 1. And 6 times 5 is equal to 30, 31, 3. And 6 times 2 is equal to 12, 15. Right? So that's basically how you do this. And then when you move on to this digit, then you have to use a 0 over here, because you're moving to the tens place. And then you will get some digits over here. When you move to the next digit, you have to use 2 zeros over here, because you have now moved to the hundreds place in this number. And then you will get some digits over here, and then depending on the number of digits that you have in this second number, you will get some zeros relative to that over here, and so on and so forth. And then what happens is that you have to basically, you will add all of these together, and then over here it's always this first digit that you got as a result of multiplying these two numbers. So this number and this number, let me actually do this in a different color so you multiplied this digit, and then you got this number over here, right? And then it doesn't matter how many digits you have over here, for those digits you're always getting zeros and zeros and zeros over here, all the way up to infinity. So it's always a question of these 3 digits. Okay, so now you need to know what sort of numbers you can have over here, and what sort of numbers will end in a 0 over here. So basically these two numbers over here, I mean any place value in any number can have at most, basically you can have 0, 1, 2, 3, and so on and so forth, all the way to 9. Of course, any digit cannot take more than a 9. And then if you have a 10, this becomes a 0, and then a 1 goes over here. So this digit can be at most a 9, and this digit can, the same goes for this digit, and it can be at most a 9. So then you could have at most 9 times 9, which is equal to 81. So then this digit can be, I mean, this number over here can be at most 81, in which case the 1 stays here and the 8 goes to, you will have a carryover 8 over here. That would be an 8, and then the 8 would be added to this number, and so on and so forth. So now the numbers that actually you need to figure out the numbers between 1 and 81 in such a way that a ends in a 0. You're looking for those numbers, and you know that the upper limit of this number can be 81, right? Is 81 actually. I mean, the highest value of this number over here can be 81, because the upper limit of each of these numbers is a 9. So now you're looking for all the numbers between 1 and 81 then that basically end in a 0. So if you look for those numbers, you have 1, 2, 3, 4, 5, 6, 7, 9, 8, 8, 9, and 10. So you have a 10, and then you have a 11, 12, 13, 14, 15, and so on and so forth. And these are actually a belongs to the set of natural numbers. So 11, 12, and so on and so forth. And then you have a 20, and then you have a 30, and then you have a 40, and then you have a 50, 60, 70, and 80. Okay? So in order to get a 10, in order to get the 10 over here, so that you have a 0 in the units place, 10 is the same thing as 2 times 5. 2 times 5 is equal to 10. 20 is the same thing as 4 times 5. So 2 times 2 times 5. 30 is the same thing as 6 times 5. 6 times 5. Or which is the same thing as basically 2 times 3 times 5. So this could actually be a candidate. 40 is the same thing as 8 times 5, which is equal to 2 times 2 times 2 times 5. 50 is the same thing as 2 times 25, which is equal to 2 times 5 times 5. And 60 is the same thing as 2 times 30, which is equal to 2 times 6, which is 2 times 3 times 5. So this could be a candidate. 3 times 2 is a 6. And 70 is the same thing as 2 times 35, which is equal to 2 times 35 is 5 into 7, so 5 times 7. But there is no possibility here to get that kind of thing. And 80 is the same thing as 2 times 40, which is 2 times 2 times 20, and 20 is 4 times 5. So 2 times 2 times 2 times 2 times 5. So you have using these factors, this kind of thing, of course, cannot happen. This kind of thing where you can get a zero there. You can get a 0 there with a 6, and since your numbers are basically 6 raised to the power n, when you have 6 raised to the power n, basically you could have one factor of 6. Basically, let's see, if you have a one factor of 6, if you have 6 raised to the power 1, for example, 6 raised to the power 1 would be 6, which is of course not what we are looking for. 6 raised to the power 2 would be, for example, 36, which is equal to 6 times 6. And okay, so if you have 6 raised to the power 3, that's 36 times 6. Again, you will end with some number with a unit place 6 over here. So you have to actually, what you have to have in order to get a 0 there is basically for example, this case would be 6 times 5. 6 times 5 in the unit place, or a 2 times 30 in a unit place, which is of course not possible. That would be, for example, a 4 times, or a, so this is actually not possible in any way. This is actually not possible in any way, because you would get 4 times 2, 4 times 2 is equal to 12 times 5, which is not possible. 12 cannot be in one basically in one placeholder, and so this is not possible. The only possible case would be this, and that's only possible if you get, for example, 6 times 5, meaning that one of your numbers is a 6 and one of your numbers is a 5. and that should happen over here. So for example, if you get a 6 over here and a 5 over here, then you'll get a 30 over here and a 3 carryover. So how can that happen? So for example, if you had 6 cube would be 36, and then the so the only way that can happen is that 6 raised to the power n can end in a 5. If 6 raised to the power n can end in a 5, then that's actually possible. And then that takes us into another line of logic and line of thought. So this is something that you could pursue if you want. I don't know. I don't want to get into the second circle, because now I moved in this circle of thought, and I got to this number 5 over here. So now, in order to figure out if this case can happen, I need to figure out if 6 raised to the power n in any case can give me a number that has a 5 in the unit place, and then that might take me into some other circle and so on and so forth. So I don't want to go there actually. But you can actually play with this train of thought that I just gave you and see where you can get with that. Sometimes you enjoy playing with numbers, but otherwise it's not. Otherwise I wouldn't go down that road. Now there is a way that you can actually solve this problem, and I'm going to show you how in just a few moments. Okay, so basically now the way that you solve this problem is actually pretty interesting. And I mean, the logic that they have used in order to solve this number is pretty neat. So we wanted to know whether 6 raised to the power n, whether 6 raised to the power n can end with the digit 0, can end with the digit 0 for any natural number n. For any natural number n. So then if basically 6 raised to the power n was basically for any n belonging to the set of natural numbers, was supposed to end in a 0, okay, was supposed to end in a 0, then what that meant was that this number was actually divisible by 5, meaning that of course any number that ends in a 0, you know that's the divisibility test for 5 anyway, for 5 and 10. So for the divisibility test for 5, we say that if a number has a digit 0 or 5 at the units place, then that number is actually divisible by 5. So that means that if this number ends in a 0, that means that this number is divisible by 5. Okay? So now if this number is divisible by 5, that means that there is at least one factor of 5 in the prime factorization of this number. That means that there is at least one factor of 5 in the prime factorization of 6 raised to the power n, right? Now, but we can check whether this 5 is there or not. So you know that basically, you know that 6 raised to the power n, you can write it as 2 raised to the power n times 3 raised to the power n. So that means that in the prime factorization of 6 raised to the power n, there is some number of, there is an n number of 2's and there is an n number of 3's in there, but there is no 5 in there. It's not possible that you can get a 5 in the prime factorization of this number. So since this is not possible, that means that it's not possible that the number is divisible by 5. And so, since the number is not divisible by 5, that means that it's not possible that the number ends in a 0. And that's basically that's your answer. So that means that 6 raised to the power n cannot end with the digit 0 for any natural number n. That's actually an interesting way of solving this problem. Or I actually came across another variation of this problem over here. Let me show you what I mean by that. So let me get myself some space over here. Okay, so basically we have another number here, and we want to check whether we have some number for example, let's take 4 raised to the power n. 4 raised to the power n, and n is basically belongs to the set of natural numbers, right? We want to check whether there is any value of n are there any values of n for which 4 raised to the power n ends with a 0. Ends with a 0. Okay? So again, if 4 raised to the power n ends with a 0, what that means is that basically 4 raised to the power n is divisible by 5. Is divisible by 5. And if it's divisible by 5, you should be able to find at least a factor of 5 in the prime factorization of 4 raised to the power n. Now 4 raised to the power n is basically the way that you can prime factorize it. So you know that you can write 4 raised to the power n, you can write it as 2 raised to the power n times 2 raised to the power n, or you can write it as 2 raised to the power 2n. 2 raised to the power 2n. That way you can also write it. So now you can see that there is, the only prime factors that you can find in the prime factorization of this number 4 raised to the power n is actually only 2's. There is no 5's in there. So that means that the number is actually, well, not divisible by 5. If it's not divisible by 5, it cannot end with a 0, and that's basically your answer there. And that's basically your answer, the answer to this question. There is another question over here that let me go through there is actually 2 more questions over here. Let me go through these 2 and then we will end this part. Okay, so there is an interesting problem here as well that I'll try to solve. If I can't, then it's up to you to solve it. So there is so here we have a sports field, let's say that this is a sports field in the shape of a I don't know, rectangle, and there is a circular path around this field, meaning that there is this path around this field and it's circular. Okay, so let me see. If it's a circular path, so I am supposed to do it in circles actually. Okay, so let me draw a circle actually. Let me draw a circle over here. Okay, so let's say this is a circle, and I go over here, border. Okay, one. Come on. Okay, and then if I'm not wrong, control this one, and then that's it. Alright, I think. Okay, so and then I deselect. So this is my circle. So let's say that there is your field is basically somewhere over here. So your field is over here. So this is your sports field, and this is a circular path all around the field, right? So now there are two persons. Let's take this as the starting point. As a starting point, there are actually two persons that basically, for whatever reason, they want to drive around this. They want to drive around this path, this circular path. So there is person A and person B that basically do the same thing. Now, person A, it takes him 18 minutes to do one complete round around to go around the circular path basically once. And person B, it takes him 12 minutes to go around the path one time. Now suppose that both of these people start at the same time, and at the same start point, and they go in the same direction, meaning both of them are going in this direction. So now what you want to know, after how many minutes will they meet again at this starting point? So what that means is that person A is going to go around this circular path, and it takes him 18 minutes. So after 18 minutes, he's going to be back here. So in 18 minutes, he's doing one round. And then this person over here, he's going to do that in 12 minutes. He's a little bit faster. So he does that in 12 minutes, and he's back here. And so that means that person B is actually reaches to the starting point before person A reaches here. So but there has to be some point, there might be some point in time where these people will meet again at this starting point. And the way that you can actually calculate that is you have to find some number. You have to find some number where that you have to find some number that is both the multiple, a multiple of this number, and also a multiple of this number, meaning that number has to be divisible both by this number and also by this number. If you find that number, then for example, let's say that number, for example, let's take that as x. Now this number is a multiple of this number and also a multiple of this number, meaning that it's divisible by this number and also by this number. So for example, if that number is x, then x divided by 18 is going to be, for example, I don't know, for example 1, and x divided by 12 is going to be 2. That means that, for example, if one person, if person A does 1 round around the field and person B does 2 rounds around the field, then they're going to meet over here at basically these after these x minutes. So now this is either the concept of LCM or HCF, right? So let's do some experiments, because I don't really know if that's the LCM or HCF. So let's say that you have, let's actually do the experiment with the same two numbers. So if you have 18 and 12, so 18 is equal to 6 times 3. 18 is equal to 6 times 3, which is equal to 2 times 3 times 3. And 12 is equal to 4 times 3. So 2 times 2 times 3. Now the LCM of 18 and 12 is equal to, again, I have to go over here. The greatest powers of the prime factors. The greatest powers of the prime factors. So the prime factors over here is basically 2 squared times 3 raised to the power 1. And this is 2 raised to the power 1 times 3 raised to the power 2. So the greatest power of this prime factor 2 is 2. So that's 2 raised to the power 2. Times the greatest power of this prime factor is 2. So that's 3 raised to the power 2. So that's 4 times 9 is equal to 36. That's 36. And if I were to do it manually, the way that I usually do it is that, for example, if you have 2 times 3, which is equal to 18, and if you have, for example, 2 times 3, which is equal to 12, then the LCM is basically some number that contains both of these numbers. So I would go for 2 times 3, and then for this number I need 2 factors of 2, so I add the factor of 2 here, and then I need 1 factor of 3, which is already there, so that's 9 times 4 is equal to 36, which is the same number. But that way, that's basically much more systematic, and actually is actually better in my, even in my opinion, it's better, although I'm not, although I sometimes or most of the time I actually forget these two definitions. But over time, if it comes up, often enough, then you will actually learn it, and that's no problem. Now the HCF is the lowest power of the common factors. So the lowest power of the common factors of 18 and 12. So the lowest power of these common factors is actually 2 raised to the power 1 times 3 raised to the power 1, which is equal to 6. So your HCF is equal to 6, right? So you see that the LCM, when you take the LCM, it's actually some number which is a multiple of both of these numbers. So what we were looking for was actually the LCM. Okay? So what that means, so now the number is actually 36, which is equal to the LCM of the two numbers 18 and 12. So now if you come over here, and it's actually in minutes. Okay? So now after 36 minutes, basically 18 times 2 is equal to 36. You know that 18 times 2 is equal to 36, and 12 times 3 is equal to 36. Okay? So what that means is that this person A, that takes 18 minutes to do one round around the circular path, if he does basically 2 rounds, he's going to be over here. He's going to be back to, after 2 rounds, he's going to be back at the starting point. And then the next person over here, person B, that takes him 12 minutes to do 1 complete round. After 3 complete rounds, 1, 2, and 3, he's going to be at the starting point. That means that person A takes does 2 rounds, and person B does 3 rounds, and then after 2 rounds and 3 rounds, after exactly 36 minutes, they're going to meet each other back here. So that's basically another application of this of LCM and HCF. Okay, so I hope that you enjoyed this video, and I will see you in the next video. Thank you.